Okay, so a few reminders. The homework for optimization is due on Monday. You also have a quiz aid that's just up online this morning, and it's on D2L. It covers section 3.7 and 3.8, and it's due this coming Sunday. We haven't talked about section 3.8 yet. That's what we're going to do today. So um, do not start until, I guess, later today. You can also find all the video notes on Piazza, and if you have any questions, just post them on Piazza. Any questions before we start? Okay. Let's do a quick review on what we talked about last time. I'm assuming everyone can hear me, right? Okay. So last time we talked about um, some optimization problems, and let's just review the usual, the standard um, techniques that we use. What do I want to talk about? Okay, I guess the first one. So the first step is always you want to write down the target function, and then the second one is the constraint. So the target function is the function that you want to optimize. So by optimize, I mean you either want maximize or minimize. Constraint, that's usually in the question. So whenever there's a number in the question, that's how you get a constraint. And then because we want to maximize or minimize, that means you want to use a constraint to change the target function into one variable function. Ugh. And then take the derivative and find critical points. So critical points are you need to set the derivative to be 0, and also need to check other points where it's undefined. And then make sure to verify it's a local max or min. So check local max and min. Any questions? Okay. Yes. So you use the first derivative test to find the critical points. Sorry, no. Wait. So to find the critical points, you set the derivative to be 0, or you check other points where it's undefined, and then you use the derivative test, either the first one or the second one, to verify that's a local max or min. It could be neither, but you have to verify it's a local max or min. Okay. Any other questions? So I want to finish up this section real quick but I want to talk about 3 examples before we move on to the next section. So the first example is the example that I included up here. I will do the whole process for this question, and then I will also talk about 2 questions from the web work, but I will only write down the equations, which means you have to do the algebra on your own. Okay, so let's look at this question. I'll give you 1 minute to read the question. Your face cam went away. What? Okay, cool. Wait, what? It's okay, but scroll down. Yeah, do that. And I guess as long as you can see my um, screen from the phone, that's fine. Yeah. Okay, so question 4. So a person wants to fence a rectangular area of 12 meters square and then divide the region in half with a fence down the middle parallel to the sides. What's the smallest length of the fencing that will be requested? That will be required to do this. So what do? What is the first step? Okay, you want to write down the target function and the constraint, right? But I usually like to draw some picture first. And what is the shape in question? It's a rectangle. It's not just a rectangle. So you see that the rancher also wants to divide the region in half. And so there should be a fence down the middle. Is it okay? Now let's put some variables in it. Let's call this one x. So the middle one should also be x, and this one is also x. The top is y. So I'm calling the total length on top y, and the same for the bottom. Is it okay for everyone? Okay, so what is the target function? What is the function that we want to maximize or minimize? Okay, so you want to, I guess you want to minimize the fencing. Okay, so this is the so let's call the fencing P, the perimeter P. So these are all the sides that you want to fence. You also want to fence the middle as well. And you have 3x and 2y. So P equals 3x plus 2y, and that's your target function. Is it okay? The constraint, there's only one point where there's a number, right? Which is 12 meters squared. And what does it describe? That's an area. The area is 12, so the area formula for the rectangle is the width, which is x, times the length, which is y. So x times y. Now, using the constraint, you can isolate one variable. Again, it doesn't matter what variable you use, and in this case, it really doesn't matter. So I'm gonna do y equals 12 over x. And then you plug this into the target function. And we get, so p equals 3x plus 2 times 12 over x. Let's try to simplify that. So you multiply the 2 to the top, which is 24, and then I'm rewriting the 1 over x as x to the negative 1. Now we want to find the critical points. And so you take the derivative, three minus 24x to the negative second. Does it have any undefined points? Okay. Actually, x equals 0 is an undefined point. But do we care about that? Yeah. Okay, so it's an undefined point. But do we care about that? Nope. So again, the total area should be 12, which means none of the x or y can be 0. So this can never happen. Which means I only need to solve 3 minus 24x to the negative second equals 0. So 3 minus 24x to the negative second equals 0. How do I solve this again? Okay, so put that to the right hand side. You get 3 equals 24x to the negative second. Divide both sides by 24, so you get 3 over 24, which is 1/8, equals x to the negative second. So 1/8 equals 1 over x squared. So remember that x equals negative second. Sorry, x to the negative second, that's the same as 1 over x squared. You can cross multiply and get x squared equals 8, which gives you x equals plus or minus root 8. This is not possible because we're talking about length, so it should be positive. Which means this is your only critical point. And how do I check that it's a local max? How do I check it's a local min? You draw a table, you can do the first derivative test. Okay, so I'm looking at p prime and p, and then the domain is from, I guess, 0 to 12, right? Oh, All right, so pick points for these two intervals and then plug them into your derivative, which is uh, this, and then check if it's check if they are positive or negative. And okay, let's see. So you have root 8. What's the derivative again? 3 minus 28, 24. Pick 1 square, which is minus negative 21. So this one should be minus, and I'm guessing this one will be positive, but you should check that. This one should be positive. So that means the function is decreasing here, increasing here, and which makes root 8 a local min. Are we done yet? So it's asking for the smallest length of fencing. Once you find out the local min, you need to plug that into the p function. So the smallest length would be p equals this, 3x plus 24 times x to the negative 1. Is it okay? What are the units? Ha. Okay, it should be meters. Remember that this is length, not the area, so it should be meters. Any questions? All right, so that was very easy, and let's look at, oh no, that's not what I want. Let's look at this question from the webbook. And I think this is question 6. Okay, so you have a line equation 3x plus y equals 2, and you want to find a point on the line that's closest to the point 1, comma, negative 4. So the 1 is the x coordinate, the negative 4 is the y coordinate. What do we do? There's no picture to draw here, so I just write down the target function and the constraints. What is the target function? What is the function that we want to optimize? Distance between 2 points. Okay. No, okay, so 3x plus y equals 2 is actually the constraint, right? It gives you the relationship between x and y. The target that we want to find, I mean, the function that we want to minimize is the distance function, because we want to find a point on the line that's closest to the point 1, comma, negative. Does it make sense? So the target should be the distance between 2 points. Do we remember? So does anyone remember what is the formula? What is the distance formula between 2 points? So the distance formula between 2 points, and let's call them no. That's a slope formula. The distance formula between 2 points x1, y1, x2, y2 is the following. So I'm calling that, I guess, d equals the square root of x1 minus x2 squared plus y1 minus y2 squared. So we have 2 points, and this is the distance formula. Okay. Coming back to the question, I know that the target should be the distance, right? And one of the point is given in the question, which is 1, negative 4. The second point, you can call it x and y, which means your distance function is something like this. So it should be x minus the x coordinate, which is 1 square, plus y, the y coordinate, minus the y coordinate of the other point, which is negative 4 square. Questions? Any questions? Okay. What about the constraint? So you want to find a relation between x and y, and that's already given in the question. So the question says that 3x plus y has to be 2. So 3x plus y equals 2. Is it okay? Okay, so you can either do this or you can do the following. So if you focus, let's just focus on this distance function for a second. So does everyone agree that to minimize this function, it's the same as minimizing this function? So I'm writing the same function, but without a square root. Does everyone agree with that? How? Um, okay, so does the root go away with nothing else? Yeah. So the idea is the short answer is whatever that minimizes the distance function, it should also minimize the function without a square root. This is always true. And I don't want to go into the details, but the reason is the square root function is an increasing function. So for an increasing function like this, you can always do this. And so we should, we still have the same constraint, which is 3x plus y equals 2. So you can either do this or this. Does anyone see why I prefer the second one? It's just a notation. I don't want to call it the same. You can pick an alphabet that you like. can call it A or something. But the question is, does anyone see why I prefer the second one instead of the first one? Okay, it doesn't have square root, which means it's easier to take the derivative with. If you don't like this, you can also do the first one. And the standard procedure is you use this constraint to isolate one variable and then plug that into your distance function and then take the derivative. But because it has the square root and also all the messy stuff inside, it's much harder to take the derivative of. On the other hand, this function right here, it doesn't have square root and it's much easier to do with the derivative. Make sense to everyone? Okay. The second question I want to look at is this. Uh-oh. Okay, I think this is web work question 8. Okay, so you have a cylinder that's inside a right circular cone. And the height of the cylinder is 12 inches, and the radius of the cylinder is 7 inches. The question is, what are the dimensions of the cylinder such that it has the maximum volume? So instead of drawing that whole thing, I'm going to focus on the triangle here. In the triangle inside that picture. So the lowercase r and the lowercase h, they are the radius and height of the cylinder, right? Am I making sense to everyone? Okay. Now the capital H, it said in the question that the capital H is 12 because that's the height of the cone. The capital R, which is the radius of the cone, given in the question, it's 7. Is it okay? Does everyone see how I got this triangle? Okay. And so this is H, sorry, this is 12. This is H. That makes this one right here 12 minus H. And let's go on to put down the two equations, target and the constraint. What is the target function here? What is a function that I want to maximize or minimize? Okay, the volume. Volume of what? Is it a cone or is it the cylinder? It's a cylinder. And what is the volume formula for the cylinder? it's pi times r square times h. So r is the radius of the base. Sorry, the radius of the base circle. The h is the height, and that's a volume formula for a cylinder. Make sense? Now the constraint function, the constraint equation, it should give you a relation between r and h. I'm gonna use this triangle here, and then the constraint is actually comes from the similar triangle property. Which basically says that, can I change color? Okay. Which basically says that this distance over this distance is the same as this distance over this distance. So r over 7 equals 12 minus h over capital H, but capital H is 12. Let me is it okay? This is a similar triangle property. Okay, and now it gives you the constraint. And again, the standard procedure is to use the constraint to isolate one variable. You can isolate either r or h. And then put that into the target function. Take the derivative, set it to be 0, or find other points where it's undefined. Check that it's a local max, and then that's it. Questions? Any questions? Okay. All right, let's move on to the new section. So the new section, the new topic, section 3.8. Well, actually, I want to stop recording